Okay, this is a video I wasn't planning on doing as part of the original collinearity orthogonalization series, but somebody asked and I'm sort of inserting it. So it may not flow as smoothly as I would have hoped with the other ones because I've recorded the other ones. But it is important for you to understand how parametrically modulated regressors are created. So it's kind of a funny story. I got up extra early today because my boyfriend had a really early flight, and I thought, oh, I'll get up and make him breakfast and coffee, send him off right? And then somebody asked this question, and I was like, well, I'm awake. I may as well do something. So some early Sunday morning work. All right, on to the topic. So the topic is parametrically modulated regressors. Typically this occurs if you have some type of value that varies with your each trial. So an example is you have not a gambling trial, but you have a trial where trial type where a subject's given a type of award. So maybe they're given a variable amount of points each time, and you expect their brain activation to modulate according to the number of points they were awarded on each trial. So my analogy is if we ignore the convolution and the fact that other things are going on, is it's just like a simple linear regression modeling reaction, and not bold data here, I'm just talking behavioral data, modeling reaction time as a function of age. So to do that, we just have two parameters in our model, right? We have a slope for age, reaction time, and importantly, we also always include an intercept. So I'm going to come back to that. And the interpretation of this is if the slope is positive, if the parameter estimate corresponding to age is positive, that means that as age increases, reaction time increases. Same thing for the bold data. We're going to have two regressors. One will take the place of an intercept. The other one will be analogous to this age regressor. And when the parameter estimate for this guy is positive, that indicates there's a positive relationship between your value and your bold activation. And I'm not going to go into it now, but typically we talked about mean centering, so you should revisit the mean centering lecture. Typically with parametric modulation, you would mean center the modulation values. Same analogy. We mean center age, so the intercept corresponds to the mean reaction time. So we would do that for modulation too. So I will possibly talk about that more later. Okay. So now let's take it to brain data. We know we model our regressors are created by taking something that looks like this. This duration, this little boxcar duration might be super short. It might be it might just be a tenth of a second or even smaller. Or it might be a couple of seconds. It depends on your stimulus. So for now, I'm assuming it's whatever this duration is here. So with an unmodulated regressor, it's assuming that the magnitude of the neuronal activation, the neuronal response for each trial is exactly the same. But you might have something, so say here they were given very few points, here they were given a lot of points, here they're given kind of a medium number of points. So you might assume that the neuron's going to fire more if more points are awarded on that trial, and less if fewer points are awarded on the trial. So we would like our model to look something like this so that it reflects this point difference. That's basically all you do. You literally modulate these, I can't believe I said literally. You modulate these according to your modulation value, in this case number of points, and then you convolve it with your HRF. So here's the example from the orthogonalization paper, which I keep referring to because that's what we're talking about. So here, as I said, we always have an unmodulated regressor, and then here we have a stimulus intensity, so this could be like the number of points. And we're also modeling RT through the modulation. I'll explain why we can do that in a second. So you can see that RT increases with stimulus intensity, but not quite the same. It's not a linear relationship between RT. So here the RT is really short for the stimulus intensity. Anyway, you can see it's not linear. And then after convolution, you get these guys. So the red one always has the same height. The blue one will change according to the RT modulation, and the green one will change according to the stimulus intensity. And the interpretation is just like your regular old regression slope. Remember I said, oh, the slope, if it's positive, it means we have a positive relationship between age and reaction time. Well, here you always have an unmodulated regressor, so I'm going to assume the order is regressor 1 is unmodulated, regressor 2 is modulated, according to whatever, and you can have more than one modulated regressor. Then this contrast, 0, 1, will test for a positive slope, and 0, negative 1 tests for a negative slope. Done. Okay, I wrote some code, and here it is. So I'm using this fMRI library. There's a whole video that's going to be using a version of this code. So I'll talk about it more then. As I said, I'm recording this after I recorded that, so I wasn't able to have as smooth of a transition as I would have hoped. But it's really no big deal. You're just going to see some of this twice. So the first problem is that there is a function in the fMRI library called fMRI stimulus. So let's look at the help for that. So to look at help, you just do question mark and then the name of the function. So I'm down here and it pops up over here. And this is cool. Actually, you might want to use this if you're running an efficiency calculation because it creates your regressors faster. Basically, it allows you to just input the typically three things, the onsets and the durations, the TR, which they call RT, number of scans. So it allows you to specify the onsets either in seconds or in TRs, and it creates a beautiful convolved regressor. These are the parameters for your double gamma. And the only snafu here is that it doesn't allow you to put in a parametric modulation. So what I did is I fixed this. So if we go up here, there's this fMRI stimulus.jm, and I just sort of tweaked their code to do what I wanted to do. I'm going to leave that at the end of this video. So that's like the last 10 minutes of this video. You should watch it though, because you can learn a little bit about R. It has a really simple tweak just to allow this extra input of modulations as well as durations. Okay, so watch that if you're interested in that. The important thing though is this regmaker function. You'll see this again. The convolution, you should do it in a finer time resolution than the TR. And I've talked about this before. Otherwise your regressor won't capture the peak correctly. Any trial that occurred within the TR would look exactly the same in the regressor. I've talked about this before. So that's all this is doing. It creates a regressor at a 0.1 second time resolution right here. And then I downsample it to the TR here. So that's really all it's doing. I wrote a function for it to make my life easier. And it used to mean center, but I'm turning mean centering off. I've commented that out here because otherwise I won't be able to illustrate what I need to illustrate. Okay, so that's all this function's doing, is it's allowing me to do that convolution in a finer time resolution because this function also didn't have that ability. Okay, so I have two functions here. I'm just going to input them. You just highlight them, and in RStudio on a Mac, you can hold Command and Return. Enters all my code. Now we can get to the illustration. Okay, so due to the linearity of the convolution operation, modulating is the same as multiplying a regressor by the same value. So here what I'm doing is I'm creating a single trial. The modulation is going to be 10, and I'm going to create an unmodulated regressor. So the modulation's 1, and then I'm going to create another regressor that is modulated by 10, and I'm going to compare the modulated regressor to the unmodulated regressor multiplied by 10. You'll see what I mean. So I'm just going to run up to here. So what this plot is showing is this thick black line is the modulated regressor. So you can see the amplitude is much higher. And this green one, oh, why is that not at 0? This green one is the unmodulated regressor. Yeah, so it's just the unmodulated regressor. So then what I'm going to do is I'm going to take this green regressor and multiply it by 10 and plot that. And it'll be a cyan dotted line. And you can see it lands exactly on top. The reason I made the black line thick and made the cyan one thinner and dotted is so you can see they're exactly the same. So just to recap, a modulated trial is simply taking a trial of height 1 and multiply it by the modulation value. That's just a simple fact of convolution. It's linear. So if you multiply that boxcar by a value before modulation, it's equivalent to multiplying the regressor by that value afterwards. The trick is you can't just simply do that when you have multiple trials of different modulations. So here I'm going to have 3 trials and 3 levels of modulation, 1, 2, and 3. And right, let's just plot it. I'll show my point here. So my point here is this is again due to linearity. So this one has a height of, this one corresponds to a modulation of 1, modulation of 2, modulation of 3. Since I'm using, again, convolution, the height of this is going to be half as big as the height of this, and the height of this will be 1/3 the height of this because the modulation values are 1, 2, and 3. Okay, so that's all it's doing. And one of the last things I want to talk about here is I said earlier that I was going to model reaction time, which we typically would think of as being a duration thing. For reasons I'll go into much later about modeling reaction time, it's actually related to orthogonalization. It is easier to model reaction time more correctly if you can model it through the modulation value. So this is just to illustrate that modeling reaction time as a parametric modulation is very similar to modeling it as a duration. So I'm creating durations of 1, 2, and 3, and I'm going to add that to this red regressor here. Okay, so again, the blue was created by changing the durations. So the modulations are all 1 for the 3 trials for blue, but the durations are 1, 2, and 3. Whereas the red line, the durations are all 1 and the modulations are 1, 2, and 3. So I've just flipped where the durations and modulations were used. And you can see those are pretty close. And it turns out in terms of modeling, you get very similar results. Right, and I will get into this later. It has to do with properly orthogonalizing reaction time when you have multiple reaction time regressors. Okay, so the conclusion here is that modulating by a value is similar to changing the duration of a modulated regressor. So an important consequence of this is if you don't model reaction time differences can look like amplitude differences in activation. So you have to be careful that you model RT, especially if you have 2 trial types that have very different RTs. You have to model out RT or else your RT differences will masquerade as activation differences. And also don't forget, just as in the age reaction time model that I showed a second ago, right here, we always include a slope and an intercept. We do the analogous thing here. We're always going to have an unmodulated regressor and a modulated. So this last chunk is just plotting those. So you're always going to have something that looks like the red one, which is your unmodulated one, and one that looks like the blue one. And as I said earlier, we're typically going to mean center the modulations, and here's why. If I don't mean center the modulations, the interpretation of the red regressor is the brain activation when the modulation is 0, which doesn't make sense in most situations. So if I take my modulations here and mean center it, then it will look like this. It looks a little weird, but now the interpretation for the red regressor is the average bold activation over the trials. And the blue regressor, even though it looks wildly different, the parameter estimate will not change. It has the same interpretation. As my modulation value increases, how does my bold signal increase or decrease? Okay, so you do that to aid in interpretation. And it's related to orthogonalizing. And when I talk about RT modeling in specific later on, you will learn more about why I'm bothering modeling it this way. Okay, so hopefully that's clear. I know I went through the code fast. Go through it slowly on your own and play with it. That's why I write the code. so you can actually see these things and create it on your own. All right, code time's over. So that's it. Actually, just after this, I'll come back to this in a second. I'm going to have now the chunk of lecture that explains how I created that function. So if you're interested in seeing that, please watch that. Otherwise, I mean, I don't know why you wouldn't watch it. It's really cool. I take that function and I add, like, I don't know, 2 lines of code, and that allowed it to do modulation. So it's pretty fun when you can do that. If you don't want to watch it, fine. No hard feelings. Please join the Facebook group, the Tumblr, or follow me on Twitter, or all 3. Thanks. And keep watching. Keep watching. There's more. Okay, earlier I said that I would come back and show you how I created that function based on the one that was already created. So the reason is because the fMRI stimulus, you can always get help in R by doing question mark and then the function name. The fMRI stimulus function doesn't have what I want. It allows you to put in the onset times, the durations of the trials, the TRs, the scans, the times. This is just, it seems redundant, but it's just because it allows you to specify the onsets either in seconds or in TRs, and whether you want it mean centered, and then all of your parameters for the double gamma HRF. Nowhere in there is there parametric modulation, and so I'm just going to make one. So in R, for a lot of these libraries that do very quick things, convolving and regressor is pretty quick, the code is written in R. If it's been written in Fortran or C, you can't access it. But luckily for this one, if you just type the name of the function and hit enter, you can get it. So if I tried something like mean, this has been written in Fortran or something else, so I can't actually access the code that computes a mean. But for this library, for this function, fMRI stimulus, it's all here. So I would like to tweak it. So what I'm going to do is I'm going, oopsie, I didn't even know it could do that. I am going to highlight this. I'm live doing this as I record. It's a big gamble. So we'll see how I do, right? Okay. So I need to put my function name, so it will be, I don't want to overwrite the original function, which was fMRI stimulus. So I am going to call it fMRI stimulus JM. I don't like using periods in function names, but that's okay. Right, and just for you MATLAB users, the period is not the same in R, it's just a character. So it's like an underscore, I suppose, in MATLAB. And the underscore is like an underscore in R too. So this is the structure of a function. You just have the function name and then function and all the input variables. Here they have an actual function within the function, and it's simply creating their gamma for them. So this is the double gamma HRF. And then it's just doing a few catches. It's converting the onset times. If you gave it seconds instead of TRs, it's adjusting for that. And it's looking for how many onsets there are. And then it's doing something else. I'm doing a bad job, right? I should sit down and figure out what all these things do, but this is just getting the number of durations and checking, yeah. So all functions have a lot of checks to make sure people input things correctly. It's a good idea to do it. It's almost impossible to catch every mistake a person could make. Okay, so here's the guts. It's just this loop, right? Let's see, where do you end loop? Down here. All right. All it's doing is it's going through all the onsets, and then it's going through, this could have been done a little bit more quickly, but that's okay. It didn't actually, you should avoid loops if you can in R, But all this is doing, so it creates a vector of zeros for the stimulus, and then it goes through and it changes the zeros that it wants to change to ones. Well, that's exactly our problem, right? We want the height of our boxcar to be something different than 1. So what I'm going to do, this is where I need to change it. This is where the unconvolved boxcar is being created. I'm going to change that to have a modulation value. So I'm going to add modulations. And I'm just following the syntax they have, where it just has a vector with a 1 in it. I should add a fancy catch here so that it's robust, but since this is just code for us, and don't, you know, if you ever do this sort of thing, don't give it to somebody as like, oh, here's this well-tested piece of code. Be like, oh, I just threw this together. It might break if you do try to do something with it that I didn't want it to do. Okay, so for example, if I forget to put in the modulation vector, it might break because all it has now is a single 1, and it's going to assume it's a vector of 1s. Oh, here, why don't we just fix that here? Actually, I'm gonna be fancy. Here's the catch for durations. I'm gonna do the same thing, but I'm gonna put modulations here. So if you put in a 1, if the length of modulations is just the 1, so if you don't put in modulations, it's going to replace modulations with a vector of 1s. So hey, I fixed it. Else if the length of modulations is not equal to the norm. Oh, good. So then if you screw up, if your modulation vector isn't the same length as the number of onsets, it's going to say, hey, you did that wrong. Oh, I feel good. Okay, I feel good because I just did the right thing. Sometimes I'm lazy, but since y'all are watching, I have to do it right. Okay, so now I have my modulation vector. It's just as long as the duration vector. It's just as long as the onset vector. All I have to do is where that 1 was. Where are you? Sorry, I'm trying not to go too much. All right, right here, instead of putting a 1 here, I'm just going to put a modulation I. Wow, and I'm going to type it correctly. Okay. Right, I. I is the current trial we're on. J, it's just marching through the onsets. Man, this really could have been simplified. I would change it, but I'm not going to. They actually could have just done stimulus and then put this in there instead of here. This should work. I'm not going to change it because maybe it doesn't work. I'm 80% sure this would work. They could have replaced this loop with let's put extra parentheses so the 1 doesn't get ignored. Here, they could have done this. And that would have worked as well. Instead of this loop, this one line of code. Avoid loops if you can. They're slow and clunky. But we're going to keep this loop here because seriously, it's going to save us time we can't even detect. All right, I'm done. That's all I'm going to do. So I'm going to enter this function. All you do is you copy and paste it. Typically, I mean, it's not going to spit out an error unless you totally screw something out. It's not actually running the code. And then I'm just going to run it using these parameters that I set up before. I'm going to cheat. I'm not going to do the, just want to know if it works. Wait, sorry. I know it's a pain when somebody's scrolling a lot. So I'm going to use this call here to fMRI stimulus. And I'm going, which in your code that we already looked at, this has already been changed. I haven't gotten there yet. So I'm recording this in a different order than I'm doing the work. Stim check equals fMRI stimulus.jm scans NTR stim onset seconds. I'm going to call this reg onset seconds. All right. Please work. Oh. NTR comb not found. NTR, oh, scans equals, how about NTR? Oh, no. Here we go. Let's see how this does. Oh, right, I forgot to put the, you know what I forgot, you guys? The whole point of doing this was to have, oh, the modulations are in there. Modulation not found. Okay, so here it says modulation not found. Ugh, means I typed it wrong up here. Sorry, I'm trying to find my loop, the function. Right here, I put modulation instead of modulations. So now don't forget you have to re-enter the function or else you're going to keep getting the same error. And we'll test it out again. Please work. The world is watching. Mismatch convolution. Okay, sorry. That's because I changed the number of TRs to match that. So here we go. Let's plot it. Oh, beautiful. All right, so that's all I did. Again, just to recap, I could have made it super simple. To do it really simple, all I did was replace this one with a modulation value, but then I got a little fancy and wanted to make the code a little more robust. So I added a duplicate of the loop used for the durations to repair the modulations vector if people input it incorrectly. And I just did a double check right here that I have a plural modulations everywhere since I had that error. Yeah, okay. Okay, for those of you who stuck around through the code, thank you again. And again, please join the Facebook group, follow on Tumblr, or follow me on Twitter, and have a really great day.